This is associated with the program on theoretical foundations of computer systems. I just wanted to briefly say thank you to Ashley Hassan, who's been doing all the logistics for these workshops in TFCS. And a big thank you also to the organizers of this workshop, Rajiv Alua, Pavel Cherny, Rupak Majumdar, and Michael Wooldridge. Thanks for all your efforts in putting things together. We'll be running this one from 9 to 10:30 most Fridays through the semester. Right, and I guess I'll hand over to Rupak to introduce the workshop.
Thanks, Peter, and welcome everybody to this seminar. So the goal of the seminar series is to get people from different communities, from formal methods, AI, reinforcement learning, and others, who have been working on various aspects of algorithmic game theory. And we have a number of very distinguished speakers, and I will send out the list also. It's already on the Simon's webpage, and I can also send out the list on the Discord server. So today we have Orna Kupferman, who will talk about rational synthesis. Just to say that, well, you know, all the speakers in this series are extremely distinguished and they don't really need an introduction. So I will be very brief and let Orna start the talk. And I will look forward to your talk, Orna. Please go ahead.
Okay, so I will start. Thank you. It's a pleasure to be in Berkeley. I will talk about rational synthesis. And I assume you know nothing, and this is joint work with Shaul Almagor, Dana Fissman, Yoad Lustig, Giuseppe Perelli, and Moshe Var. And one good thing about our area in general, if I will be able to move the slides, yes, is that the motivation part is very easy. We want the answer to this question, is the system correct, to be yes. And in synthesis, it is yes, because in synthesis we get as input a specification psi, something that describes the desired behavior of the system. We press a button and we get as output a system satisfying psi. So the answer to the question, is the system correct, is yes, because at least it satisfies its specification. So we have motivation. What do we do in synthesis? So here is a very simple example. If the specification is a conjunction of two atomic propositions P and Q, then a possible output will be a system which is really a single state in which P and Q hold. So this tells us nothing except for the fact that our system, in order for the specification to be synthesizable, it has to be at least satisfiable. Synthesis goes hand in hand with satisfiability. Clearly, if a specification is not satisfiable, then we cannot have a system that satisfies it. So once we understand this, we can check a more complicated example. Suppose they have two users and they want to print jobs. And here's the specification to my system. Whenever user I sends a job, the job is eventually printed, and the printer does not serve the two users simultaneously. In order to automatically synthesize it, I have to formally specify these requirements. So I will use 4 atomic propositions for job 1 and job 2 being sent. So this is J1 and J2, and also print 1 and print 2. And I can specify in LTL, and it's not important if you're not familiar with LTL, but this is just the LTL specification of the requirement above. So always job 1 implies eventually print 1, always job 2 implies eventually print 2, and always not P1 or not P2. And once we have this, we can check satisfiability and synthesize a scheduler that satisfies the specification. But it is not hard to see that even if the specification is satisfiable, it will tell us nothing about the existence of such a scheduler. So, whoops, something here happens now. And a model for psi will not help us to construct a scheduler Here is an example for such a model. Yes, a very boring model, a model in which no jobs are asked to be printed and no prints happen, so the specification happens, but this is not what we wanted. And this is not what we wanted because a model for psi is really a scheduler that is guaranteed to satisfy psi for some input sequence. In this example, it's a very boring input sequence, no jobs are sent. And what we really want, we want a scheduler that is guaranteed to satisfy psi for all input sequences. So it's not really satisfiability, and this has to do with something that you probably know. We'll make it very quick, the distinction between closed and open systems. So in a closed system, we have no input. Every moment in time, some output is generated. Think about a counter. Still, we can synthesize closed systems, and in that case, since there is no input, all input sequences is the same as talking about some input sequence, and then synthesis goes hand in hand with satisfiability. But what we really want is to synthesize open systems, and open systems interact with an environment. In each moment in time, some output is generated, then an input comes, another output, an input, another output, and you can see the outputs depend on the inputs. And in general, we no longer have just a set of atomic propositions, but we distinguish between input and output, signals or propositions. And the system, an open system, is no longer just a labeled state transition graph, but it is a strategy, something that maps sequences of assignments to the input signals, the history of the interaction so far, to the next assignment to the outputs. And so this is a general strategy, and we care about regular strategies. So no matter that, that's one definition. The convenient one is that a regular strategy is really one that can be represented, can be generated by a finite state transducer. A finite state machine, it has inputs on the edges, and inputs, I mean assignment to the input signals on the edges, and assignments to the outputs in the states. So what is really synthesis? We want these strategies. In the printer example, the inputs are the jobs being sent, and the outputs is the decision which of them is being printed. A strategy is something that maps finite sequences of assignments to the inputs to assignments to the outputs. And now we don't talk about satisfiability, but we talk about realizability. What is realizability? An open system has a computation, something that starts with whatever the strategy returns for the input, for the empty sequence of inputs, then the first input and the first output, the second, yes, I1, f of I0, I1, and so on. And we say that the specification is realizable if there is a function such that all computations of f satisfy psi. So whatever the green inputs are, the strategy f assigns red outputs so that the joint computation satisfies psi. So this is called realizability. And the important thing for us is that an important system, an open system is correct if it satisfies its specification in all environments. So it's not satisfiability, it's realizability. And this all environment requirement may be very strong. Sometimes it is too strong. It is too strong, and again, already 2 decades ago, researchers have noticed that we not want the specification to hold in all environments, and they added assumption on the environment. And these assumptions may be behavioral, just other LTL formulas that tell us that the specification has to hold only in environments that satisfy this or that condition. So these are behavioral assumptions. And we can also talk about structural assumptions. And these are things like, we know that the environment has at most k states. Yes, so a structural assumption on the environment that generates the input. And rational synthesis, the thing I'm going to talk about today, belongs to this class of assumptions on the environment. But the assumption is different. It is not behavioral, it is not structural. Rather, it says that the components that compose the environment have their own objectives and are rational. So this is rational synthesis. We will define it more formally, but the idea is that we don't want, or we don't require the system to satisfy its specification in all environments, but only in rational environments. And soon we will define exactly what it is. So rational synthesis, here is an example. So assume we have, again, two users. It need not be the same users from the previous example. And now these users want to upload and download. So they have these input and output signals. Soon we will see exactly the connection. User one, it generates upload one and download one. So U1 and D1, but user one can upload only when user two downloads. The other way around, sorry. So this is a typo. User one, think about download as get. So user one can get only when user two gives. User two can download only when user one uploads. So that was a typo, but in the specification soon it will be corrected. And both users want to download infinitely often. So if we specify it with LTL, so if my typo confused you, so think about this objective. User one wants infinitely often to download D1 and U2. So user one wants that infinitely many times simultaneously. She downloads while user two uploads. And in a symmetric way, the objective of user two is to infinitely often download two while upload one. Okay, because we can download only when the other user uploads. So this is the specification, and you can see that the objective, so we are now user one, we want infinitely often to download while the other user upload, and this is not realizable. It is not realizable because it fails, for example, when user two never uploads, right? So for user one, the signals generated by user two are inputs. And if user two never uploads, she cannot download. So this is not realizable. But think about, now we add rationality to the game. And we say the following: user one knows that user two also wants to download. And user one also knows that user two can download only when she uploads. So user one says to user two, I will upload. In the first moment in time, U1 will be on, and I will continue to upload as long as you upload. So this is my strategy. My strategy is to upload in the first time unit and continue to upload as long as you continue to upload. Now, a rational user two that wants to satisfy phi2, her specification, will upload forever and will enable user one to satisfy phi1. So this is intuitively, soon we will formalize it further. So, but this is the idea of rational synthesis. I am going to assume that the environment is rational and I know what the objective of the environment is. And then I suggest a policy hoping that the environment will follow it. So let's formalize it. So rational synthesis, we have a k plus one player. So player zero is us, it's the system. And then k other players. And we assume that each of them has a set xi of signals. So there is x, the set of all signals, and it is partitioned among the players, x0 up to xk. Player I assigns values to xi. What is the input to the rational synthesis problem? It is objectives psi. This is the objective of player zero. Player zero is special. Yes, this is the system, this is us. And then also objectives that the system knows about the other players, the components that compose the environment. And these are phi1 up to phi k. So this is the input. In usual synthesis, we have, yes, only psi. And we don't care about the objectives of the environment, right? In usual synthesis, the objective of the environment is just to fail the system. Now we add rationality, so we have real objectives to the components that compose the system. These are phi1 up to phi k. So this is the input. And what is the output? I want to output a stable profile. A profile is a vector of strategies, one for each player. So a strategy F0 for player 0 up to a strategy Fk to player k. And we want this profile to satisfy psi, right? If I have strategies to all agents, then together they generate a truth assignment to all the variables in X. And we want the generated computation, the outcome, to satisfy psi. So this is rational synthesis. Now I said that we want a stable profile. What is stable? Stable intuitively, and soon we will formalize it. We want the players that we do not control, right? We control P0 because we are P0, we are the system. But we want the other players, these that compose the environment, to have no incentive to deviate from this strategy because it's good for them. So this is rational synthesis. This is one variant. Why do we need two variants? Yes, this is the variant we said, and we said that we want to generate a profile that satisfies the specification, but we assume that somehow we can suggest a strategy to the environment. Sometimes we cannot. Sometimes we cannot. This is why we had two papers on rational synthesis. The first paper is cooperative rational synthesis, and this is the variant I mentioned, that we return a profile. We suggest strategies to the other players. In the non-cooperative variant, and this is with Perelli and Vardi, we have the same input, but now the output is a strategy only for us, only F0, but we want this strategy to be such that every stable profile with this strategy, so no matter what the other agents do, as long as they are rational and the profile is stable, the outcome would satisfy psi. So this is the non-cooperative variant of rational synthesis. And let's try to understand how different they are and why we really need two definitions. But again, yes, so in the cooperative variant, we return a profile of strategies for both us and the environment. And we know that if the environment is rational, then it will follow the suggested strategy. In the non-cooperative variant, we generate only a strategy for us, and we know that whatever the environment does, if the environment is rational, we will get an outcome that satisfies the specification. And when we want to understand how different they are, we look at things that people did in algorithmic game theory. So now I'm starting to talk about something that will sound not related, but will be related because it will formalize better all the notions that we need. Before that, any questions? Okay, so we continue to concepts from algorithmic game theory that will be useful also for us. And we will talk about network formation games. So what are network formation games and why they are related? So when I say network, I refer to this. So a network is a graph. It has vertices, but we call them locations. And it has edges, but we call them communication channels. And each channel is labeled by the cost of creating this channel. So this is a network. And in a network formation game, we have also players, and players need to transmit messages between locations in the network. An example, suppose we have two players, Bart and Lisa, and they need to transmit messages from location S. Bart, player 1, needs to reach A, and Lisa needs to reach B. And now they have to find a route for their messages. So the strategy space of Bart, so he has two possible ways to route messages from S to A. One is the pink one. It involves two channels, right, from S to V and from V to A. And another is to take one channel, the purple one. So this is the strategy space of Bart. He has two possible strategies in order to transmit messages from S to A. Lisa also has two possible strategies. She can either go on the purple one or the red one. And together, they have profiles. A profile is a choice of a strategy for each player. In this game, there are four possible profiles according to what each of the players, the strategy of each of the players. And let's see what are the payments. So it's easy to see that if, for example, I don't know if you see the, when I move the cursor, do you see it?
Yes.
Yes, okay. So here, for example, Bart takes the 10 channel and Lisa takes the 7 channel. So it is very natural that Bart will pay 10 and Lisa will pay 7. And if Bart takes the two edges, the two channels here, then he would pay 9, right? Why 9? Because it's 8 plus 1 and Lisa 7. And here she will pay 10 and he will pay 10. And the important thing is here, how is cost shared, right? If Bart, they both use this channel, the channel that costs 8, how is cost shared? And the easy thing to do, and this is called, I forgot how it is called, they share, I think, uniform share or something like that. So uniform share means that players that use the same channel share its cost. In our example, Lisa will pay 6 because 8 will be divided plus 2, and Bart will pay 5. And this is what we are going to get. So these are the 4 possible profiles in our example. So we know what profiles are. And now let's define best response dynamics. Best response dynamics is a local search method. In each step, some player is chosen and plays his best response strategy, given the strategies of the others. And best response dynamics converges when no player wants to change his strategy. Example, so assume that we are in the same network we saw and the player starts from this profile. So the cost for Bart is 10, the cost for Lisa is 7, and we apply best response dynamics and we do it repeatedly. So we start from example with Lisa and we ask her, Lisa, do you want to change strategy? Will Lisa change her strategy? No, because now she pays 7. If she changes her strategy, she will have to pay 10. So she has no incentive to change her strategy. So we ask Bart whether he wants to change his strategy. Now he pays 7. If he moves, he will pay only 9. So yes, so Bart moved, and this is the current profile. And now we ask Lisa again, because of course, the fact that she didn't want to change her strategy earlier doesn't mean that she wouldn't want to change it now. And indeed now, when we asked her, she will want to move because now she will pay 6. And when she moved, the cost for Bart changed too. And we will ask him whether he wants to change, and he wouldn't. And again, Lisa wouldn't. And we have reached a stable profile. A stable profile when no player has an incentive to move. Formally, a stable profile is a Nash equilibria. There are other, what people in game theory call solution concepts. We are going to talk about Nash equilibria, at least in almost all of this talk. And the Nash equilibrium is a profile of strategies such that no player can benefit from changing to another strategy, assuming that the other players stay with their strategies. And now there are all kinds of interesting questions we can ask. For example, we can ask whether best response dynamics always converges. The answer is yes. In all network formation games, if we start with some strategy and let the player do their best response, then eventually we will reach a Nash equilibrium. How do we prove it? We prove it with potential functions. We are not going to talk about it, but the answer is yes. There is always a Nash equilibrium, and we can always get to it by letting best response dynamics act. Will we reach a good Nash equilibrium? Now, what is good? Good, it makes sense to refer to some social optimum, a profile that minimizes the sum of the payments of all players together. And when we ask whether a profile is good, we ask whether it is equal or at least close to the social optimum. And if you want to view the social science aspect, it is like how much do we lose from the absence of a centralized authority, right? Rather than letting the players choose their strategies, I could come and say, Bart, you go from here, Lisa, you go from here, because I need to arrange these channels if some authority pays for these channels. And this will be the social optimum, because the authority will find the cheapest way to do it, to satisfy all requirements. But the point in game theory is that we don't have such a centralized authority, and we let the player play in a selfish way, aiming to minimize only their payment. So a very interesting question is whether this is good, whether they will pay much more, or all of them together, whether they will pay much more than whatever they could have paid with some centralized authority. So how much do we lose? In our example, we didn't lose. In our example, the social optimum was 11, and also the cost of the Nash equilibrium was 11. In general, if we want to compare the payments of the players in a Nash equilibrium and the payments of the players in a social optimum, there may be a difference. We need not reach a good Nash equilibrium. Here is a simple example. Suppose this is our simple network. It has, you can see, one source, one target, but two possible channels. One of them costs K, one of them costs 1 plus epsilon. And assume we have K players, and they all want to route from S to T. So all the K players start in the channel. This is our starting profile. All the K players start in the channel that costs K. And we say that they share the cost in an evenly. So each of them pays 1, right? Because we have K players sharing a channel that costs K. We divide the cost, so each of them pays 1. This is a Nash equilibrium. This is a Nash equilibrium because each of these K players say, now I'm paying 1. If I switch, I would need to pay 1 plus epsilon, because when we define a Nash equilibrium, the other players stay. Yeah, so it's not that two players together move. We always ask about one player deviating from the current strategy. So no one wants to switch, and this is a very bad Nash equilibrium. And we got that the price of anarchy, that's the ratio between the worst Nash equilibrium and the social optimum. And the price of anarchy here, this is an example where it is K, the number of K players, because, right, the social optimum is 1 plus epsilon. In the social optimum, all of them will use this channel. So the price of anarchy is K, but a good Nash equilibrium does exist, right? If the players, all of them, would have started here, no one would deviate. So now we can ask whether there always exists a good Nash equilibrium. And the answer is almost. For every network formation game, there exists a good NE, Nash equilibrium, one whose cost is at most HK times SO. HK, this is the case harmonic number. It's the sum of this sequence, which is more or less ln of K. So it's not that there is a Nash equilibrium that would give me exactly the cost of the social optimum, but the factor is not too painful. It's only ln of K. And this is called price of stability. Price of stability is the ratio between the best Nash equilibrium and the social optimum. So in network formation games, it is ln the number of players, ln k, and this is tight. This is tight, and here is a cute example. Here is a network, and assume we have 4 players, and they all want to route from S to the green vertices, right? So player 1 wants to route to T1, player 2 to T2, and so on. And let's see what's the social optimum, right? If we are the authority and we want to satisfy the need of the 4 players to route from S to T1 to T1, what will we do? We will construct, first let's see that each player has 2 possible strategies, right? Each player can either go on a direct edge from S to T2, let's for example, if we are player 2, or go from the green channels here. For here, we pay 1 plus epsilon, and this channel is free, right? So each player has 2 possible strategies, direct edge or via the vertex at the bottom. And the social optimum, if we are the authority, we will create, this is why it is called, we will form, this is called the network formation games. So we will form these red edges, and we will pay 1 plus epsilon for the outer edges, and then 0 for here. And in this profile, each of the players pays 1 plus epsilon over 4. Right, so it's a quarter plus some epsilon, and this is the social optimum. Questions? So this is the social optimum. Is it stable? No, this social optimum is not a Nash equilibrium. Who is going to deviate? Player 4. Player 4 will say that why player 4 now pays a quarter plus some epsilon. So he wonders, why do I pay a quarter plus epsilon if I can pay exactly quarter? Because player 4 can also go on this direct channel, direct pass, and pay only 4. So player 4 is going to leave this profile and route the messages on these strategies. And again, we are not stable. We are not stable because now each of the players pay a bit more than 1/3. So player 3 will say, why do I pay a third plus epsilon if I can pay exactly third? And we'll move here. So now we have 2 players on this edge, and these 2 players, each of them pays a bit more than half. So player 2 is going to deviate, and then player 1 is left alone on this edge, pays 1 plus epsilon, and he will move here. And this is the stable profile we get. And this is the only, actually, Nash equilibrium we have in this network. And the cost of this Nash equilibrium is the harmonic number. I gave this example with 4 players. We can do it with any k players, and then the price of stability will be 1 plus half plus third plus 4 and so on. And so there is no perfect Nash equilibrium. So soon we will be back to rational synthesis. Just like, let's see what we learned. So we learned that in network formation games, players have reachability objectives. Players that share a channel share its cost. The notion of Nash equilibrium in network formation games, it's a stable profile in which no player has an incentive to change his strategy. It always exists in network formation games. There is a social optimum. This is a profile that minimizes the player's payment. And we learned 2 notions: price of anarchy. This is the ratio between the worst Nash equilibrium and the social optimum. And in network formation games, it's the number of players. And price of stability, this is the ratio between the best Nash equilibrium and the social optimum. And in network formation games, it is ln the number of players. Questions? So back to rational synthesis. So in rational synthesis, what we are going to do is to see these notions, right, in rational synthesis, more or less. So in rational synthesis, we also spoke about stable profiles, right? This is the profile we want them to satisfy psi, the specification. So what is a stable profile? I want that for every player I, if the objective phi of player I is not satisfied in P, then phi is not satisfied also in the profile P when I gets the strategy F prime I. So this is a notation, and this notation is for the profile obtained from P by changing the strategy of player I to F prime I. So a profile is stable if for every player I, if phi is not satisfied in P, then it is not satisfied also in every profile I would get if player I changes her strategy to an alternative strategy F prime I. And then the reason it was somewhat easy to formalize it is that the objectives are Boolean, right? When we say an incentive to deviate, it means that the satisfaction of my objective, it was false and it now becomes true. Yes, if phi was false in P, in order to deviate, to have an incentive to deviate, I needed to change its satisfaction value to true. So the objectives are Boolean, and okay, I mean, logic is Boolean in general, computer science is Boolean, we have zeros and ones, but in network formation games, the objectives were quantitative, and in general, in game theory and algorithmic game theory, things are much more interesting because the story is not Boolean. We have quantitative objectives. So let's add quantitative objectives also to synthesis, and we have many good other reasons to do it because satisfaction is not really Boolean, right? If I consider this specification, always request implies eventually grant. So here are many computations. The first one does not satisfy the specification. Yes, request is red, grant is green. So here I have a request with no grant. Here I have a request that is followed by a grant, and again, a request followed by a grant, and so on. And if I just do a model checking, I just evaluate this specification in the these different computations, I will get false for the first and true for all the rest. But these truths are not the same. Right here, for example, I have a grant that is that I'm getting immediately. I want to give it a high grade. I will give it 1. Here I have a grant with a request with 2 grants. I don't want to give it a high grade. Here nothing happens. Here there is only grant with no request. I don't know how to refer to it. And I don't know because the Boolean setting does not distinguish between the different ways in which a specification is satisfied. So one thing we will do is to move to specify quality, to specify behavioral quality. And this is joint work with Shaul Almagor, Udi Boker, and these are logics, LTLF and LTLD, multi-valued extensions of LTL. In these formulas, for example, LTLF, the satisfaction value is a real number in the range between 0 and 1. So 0 is very bad and 1 is very good, but I can specify also things in between. So F, I said it is LTLF. F is a parameter. It's a set of, we call them propositional quality operators. Each such operator maps K values to a single value. So if this confuses you, just think about minimum. Minimum is an operator that gets 2 values in the 0-1 range and returns 1 value. Yes, so this is a case where K equals 2. And minimum, intuitively, it's like AND, right? But I want now to have a multi-value. So if I say X and 1, X and Y, the truth value of X and Y will be the minimum, or is max, negation is 1 minus, and the more interesting thing, and soon we will see examples, but the semantics, so we are going to use pi psi in these brackets to give the satisfaction value of psi in a computation pi. So the satisfaction, it is defined by induction on the structure of the formula. The satisfaction value of true is 1, the satisfaction value of false is 0, the satisfaction value of an atomic proposition P is either 1 if P holds in the first state in the computation, 0 if not, and I can also handle atomic propositions that have multi-valued, but let's not bother with it. This is the new propositional quality operator. So if I have some function, then the truth value, the satisfaction value of f of these values, and again, think about min and max or other things, is just an inductive application. Next is what you expect. Next, phi1 is the truth value, the satisfaction value of phi1 in the suffix of the computation. And phi1 until phi2, here it is, phi1 until phi2. So what is it in the Boolean case? In the Boolean case, I do a big OR on all futures, and I is a future where I want that in some future, phi2 holds in pi I, and phi1 holds in all the futures before I. So this is the well-known semantics of until. When we do it in a multi-valued way, it is what you expect. I am again taking the max. Max is like OR, right? So I'm taking the best future for me, the max over all i's, and then the minimum of the satisfaction value of phi2 in the suffix pi I, with the minimum of all the satisfaction values of phi1 in the suffixes before that. Yes, so for example, if the values of phi2 in these computations are here 0, here 0, here 0.3, and so on, and the satisfaction values of phi1 in this computation are as in the red one, what would be the satisfaction value of phi1 until phi2? If I choose I to be this position here, then it will give me 0.3, the minimum between 0.3 and 0.5 and 0.5. So I'm getting 0.3. But, and this is interesting because this is something that we don't have in the Boolean case, sometimes it is beneficial not to take the first place where phi2 is not 0, right? If I take this position here, then the truth value of phi2 is 0.6, and the truth values of phi1 in all these is 0.5. So the truth value of phi1 until phi2 is 0.5. And I can check other cases. Right here I have 0.8, but in the 0.8 here, I will again get 0.5 because of phi1. Okay, so this is a multi-valued variant of LTL, and it becomes interesting with the quality operators. Here are two examples: delta lambda, or this is nabla actually. I think, well, whatever this triangle is with lambda, it will tell me that the satisfaction value of pi with this triangle parameterized by lambda phi is, lambda is a number in 0, 1. So I multiply the satisfaction value of phi in pi by lambda. And I can also do weighted average. The satisfaction value of the weighted average parameterized by gamma of phi1 and phi2 is lambda times the satisfaction value of phi1 plus 1 minus lambda, the satisfaction value of phi2. And with these quality operators, I can prioritize different behaviors. For example, the satisfaction value of phi1 or nabla 3/4 phi2. If phi1 holds, the satisfaction value is 1. If only phi2 holds, then the satisfaction value is 3/4. If none of them holds, the satisfaction value is 0. Consider, for example, always P implies next Q or next Q. I can, with LTLF, say more. I can say things like always P implies next Q or half next Q. If I have, after every P, 2 Qs, the satisfaction value will be 1, only the first 1, only the second half. If I have this weighted average, then with 2 Qs, I will get satisfaction value 1, only the first 3 quarters, only the second quarter, and so on. So back to rational synthesis, the important thing, yes, is that we now have a way to let the designer specify all kinds of priorities about how the specification is satisfied. And okay, this is not a talk about LTLF, but algorithms for LTLF are almost as easy as algorithms for LTL. So it's, from the algorithmic point of view, use LTLF. It is not going to cost you much more, and it is much more useful. In particular, in rational synthesis, now when we talk about a profile being stable, now we want to say that for every player I, if the satisfaction value of the objective of player 1, I, P phi I is V for some value V, then the satisfaction value of phi I in every profile P prime obtained by player I changing her strategy is not more than V, right? So a profile is stable if every player, for every player I, deviating is not going to increase the satisfaction value of her objective. So if I have a profile P, the same concepts we had from network formation games, let's see how they transform to rational synthesis. So in a profile P, I can talk about the utility of P, which will be the sum of satisfaction values for all the players together. And I can also define utility by the eyes of the system if I refer only to the satisfaction value of psi. It's easy to move between these two variants, so let's stay with this one. So the utility of a profile is the sum of the satisfaction values. The social optimum is a profile in which I'm getting the max utility, the maximal satisfaction value for all the components of the system. And note that in network formation games, it was dual, because in network formation games, we talked about price, about cost, right? So we wanted to minimize it. So the story is going to be the same, only dual, because now we want to maximize the satisfaction value, and there we wanted to minimize payment. So don't let this disturb you, right? We are just dualizing the min and max, and accordingly, the price of stability, it is going to be the ratio between the social optimum, the maximal satisfaction value that all players can get together, the ratio between this and the utility of the best Nash equilibrium, and price of anarchy, this ratio for the worst Nash equilibrium. So these are the concepts of rational synthesis, and we want to understand what are they in rational synthesis, and also what is the relation between cooperative and non-cooperative rational synthesis and all these concepts. So I remind you that in both cooperative and non-cooperative rational synthesis, the input are objectives for the system and the components that compose the environment. In the cooperative setting, we wanted a stable profile that satisfies psi. So sure enough, we are going to generate the best stable profile, the best Nash equilibrium. So when we analyze cooperative rational synthesis, we will really analyze a price of stability and best Nash equilibrium. In the non-cooperative setting, where the output is a strategy F0 such that every stable profile satisfies psi, so we need something to hold in all profiles, also in the worst Nash equilibrium. So this is going to be related to the price of anarchy. So what are the prices of stability and anarchy in rational synthesis? How much do we lose from the fact that we have an environment? Let's see. So let's start with price of anarchy, and it's an example. And in these examples, assume first that we care only about the environment in the beginning. So we have k processes, P1 up to Pk, that compose the environment, and each, either process or player, they both start with P. So Pi assigns value to a single signal, to Xi. Yes, so P1 assigns value to X. P1 assigns values to X1, P2 to X2, and so on. And what are the objectives? What I'm going to show you now, I'm going to show you an example where the price of anarchy is very high. In fact, it is going to be unboundedly high. And we assume that the objective of player I, phi I, is ignore this alpha to start with. Yes, so the objective of player I is that Xi holds and Xk does not hold. So each player in 1 to k minus 1, so almost all the components in the environment want their signal to hold and Xk not to hold. And if Xi and not Xk, then they will be rewarded alpha dollars, right? Because I have this nabla alpha, so the satisfaction value of this formula, if it holds, is alpha. What is the objective of player K? The objective of player K is beta times Xk or all other Xis. Okay, so the objective of player K is that either his signal Xk valid or the X's of all other players are valid. What is the social optimum, right? If you are the authority and you can assign values to all X's, which values will you give them in order to maximize the utility? You will do this. The social optimum assigns true to all X's between X1 to Xk minus 1, and to Xk it assigns F. Why is it the social optimum? Because we will get the maximal utility. We will get utility 1, right? Because phi1, all the phi i's for I between 1 and k minus 1, they hold because Xi holds and not Xk also holds. So all these formulas will get alpha, and alpha is 1 minus epsilon over k minus 1. So for each of them, I'm going to get alpha. Phi k also holds because this conjunct is true. So player k is going to get beta, which is epsilon. And together you can see that if you take 1 minus epsilon over k minus 1 and you multiply it by k minus 1 and you add epsilon, then the sum is 1. So in the social optimum, everyone is happy, everyone is getting the maximal value that their objective can get, and no one is going to deviate. Now, this is the social optimum, but there is also a very bad Nash equilibrium. And what I'm showing you now, if you remember the network formation games, yes, this is like the case where they all were on the very bad, on the very expensive channel, but didn't want to deviate. So this is this assignment. If we assign false to all Xi's and true to Xk, this is a very bad Nash equilibrium because the players 1 to k minus 1 are not going to satisfy their objective, and they cannot deviate and satisfy it because deviating alone wouldn't help them. Xk is true, so not Xk is false, and they have to satisfy both Xi and not xk in order to get a reward, in order to get alpha. So the first k-1 players are not going to deviate. They are going to contribute 0 to the utility. Player k will satisfy her objective, will get beta, but beta is also epsilon, or is only epsilon, so the utility is epsilon. So all in all, we get that the utility is epsilon in a Nash equilibrium. It could have been 1 in the social optimum. So the ratio is 1 over epsilon, and this is unbounded. I can define these alphas and betas with any epsilon I want. The story is the same. So price of anarchy is unbounded. So environment can make us a very difficult life. Yes, because here I talked only about P1 up to Pk, but assume that the objective of P0 is, for example, the conjunction of all these, or the sum of all these objectives. And now, if you consider the social optimum, in this example, is it stable? It is stable, right? No player has, this is the social optimum where we assigned true to all x's between 1 and k-1. No one is going to deviate, so it is stable, so it is also a best Nash equilibrium. And this also teaches us that the ratio between the best and the worst Nash equilibrium is unbounded. So cooperative rational synthesis may be unboundedly better than non-cooperative rational synthesis. I also have an example for the price of stability. Again, let's skip it. Again, it is unbounded. So even if I can suggest the players which strategy to follow, I can do unboundedly worse than what I could do if I had control on them. So to sum up, when we do synthesis of open systems, we need winning strategies in a zero-sum game. Because you're right, in the traditional definition of synthesis, the environment is hostile. The goal of the objective of the environment is to fail the specification. So this is a zero-sum game. When we add rationality assumption on the environment, we have a transition to non-zero-sum games, right? Because now the objectives of the players need not contradict each other. So in the eyes of game theory, what we did when we moved from synthesis to rational synthesis is to move from zero-sum games to non-zero-sum games. In classical game theory, we have many things to take from it. The fact there are quantitative utilities, notions like price of stability and price of anarchy. Once we move to LTLF, we have quantitative specifications, and cooperative rational synthesis corresponds to price of stability because it corresponds to best Nash equilibria. But still, it is unbounded, the price of stability. Non-cooperative rational synthesis corresponds to price of anarchy, and again, it is unbounded. So this is what we saw. We didn't see many related things. We didn't see how to solve rational synthesis, connection with strategy logic, tree automata, playing games. So there is an algorithm, right, that solves these problems. There is a nice notion of rational verification. So not rational synthesis, but rational verification, which asks whether a system S satisfies psi in every rational environment. I see that the word environment is missing. There is a notion of fixing systems. So traditional fixing, correcting, yes, of correction of systems used to be by let them satisfy their specifications. Now we can talk about either fixing them in a rational way or fix them just by making them stable. They were sometimes there is no Nash equilibrium. How to change systems in order to make sure that there will be a Nash equilibrium. There are richer settings with incomplete information, with probability, and with other solution concepts. I saw that Raskin is going to give a talk about the sub-game perfect equilibria rather than Nash equilibria. There are dominant strategies, so other definitions of stables, and that's it. Thank you.
Thank you very much. I will clap for everybody. If you would like to ask a question, perhaps you can just put a Q or a question mark on the chat, and then I can call upon you one at a time. If you're an attendee, then I think you can still ask a question in the Q&A channel, but also if you want, I can sort of promote you to a panelist, and then you can ask directly. Are there any questions? So maybe I can start with one while the others are thinking of their questions. So your final slide that shows that this price of anarchy or the price of stability can be arbitrarily bad. Mm-hmm. Does this mean that this is not a good concept for system design? Because you can get into situations where you can synthesize something that's arbitrarily worse than a centralized solution.
It is, I mean, it just says that life of an open system is hard. It is still, life is difficult. I'll just switch to that example. I mean, whatever we do, we are in a better position than in usual synthesis, where we have to satisfy the specification in every environment. So it mainly says that sometimes the help we get by this assumption of the environment being rational is not that helpful. Yeah, but so it's not that it's a bad notion. It just says that life is difficult even when we assume rationality. There are settings where life is difficult even when we assume rationality, and even when we assume that we can suggest a strategy to the other components.
Any other questions?
Yes, can I ask a question? So,
yes, please go ahead.
You presented this multi-valued variant of LTL. Do you know of any such extensions for logics like mu calculus or CTL?
No, I don't. And I believe I would have known, but I don't know. For LTL, in addition to the extension of these propositional quality operators, we also have discounted operators, but still in LTL, things like until that is discounted by some function, which means that the longer you wait for the eventuality to become true, the lower is the satisfaction value. But I don't know about CTLF, and I mean in fact in the journal version we added a section that it is possible to define it, things like that, but no serious study.
Okay, thank you.
Jean-François, you wanna unmute yourself?
Yes, I can maybe. So thanks, Orna, for the talk. So I was wondering if so for LTL, so you have a version with the discounted as you just mentioned. So can you solve the rational synthesis problem for that version?
We didn't check for. I believe it will be much more complicated because in even synthesis that is not. I mean, my answer would be that the solution will probably be of the same complexity as usual synthesis.
I see. Yeah.
But even for usual synthesis, there are difficulties in LTL with discounting.
Okay. Yeah, because
LTL,
multiple dimension and discounted sum game with multiple dimension, it's a difficult problem, yes.
Right. In LTLF, since we have a finite number of possible truth values, it is easy to extend current algorithms.
I see.
With discounting, it becomes more complicated.
Okay. Thank you. Thanks.
Anna?
Yes, I have a quick question actually on the slide that you have open right now. So for me, you say that the non-cooperative version corresponds to the worst Nash equilibrium. And maybe you can explain again why this is the case. So but for me, it's not really obvious that if I fix F0 such that you get the worst Nash equilibrium, that I don't have to change F0 in order, like if the others don't pick the strategy corresponding to the worst Nash equilibrium to get another Nash equilibrium. Do you get
the exact definition we have, we define what we call a controllable Nash equilibrium. In a controllable Nash equilibrium, some of the players can deviate and some cannot. Why? Because we have control on them. So when I say a Nash equilibrium here, I mean when the other players, because I have control on the system. The system is not going to deviate because it's me. So when I say a stable profile, I mean a profile in which players 1 to K have no incentive to deviate. And I'm staying in F0. And,
okay.
and it makes sense. It makes sense in our story because if I have, when I am a system, I'm going to commit on my strategy, and the other players are going to, because my strategy is like, think about this is the piece of software I'm going to release. And then I have the other players, I can only count on their rationality.
Okay, that makes sense.
But you're perfectly right. You're perfectly. I didn't want to. I mean, you caught me on something that I wanted to skip in order to make things simple. In the paper itself, we define what is a controllable Nash equilibrium when only some of the agents may deviate.
Okay, thank you very much.
Thank you.
Any other questions? If not, then let's thank Orna again. And I think we can go to the gather thing if you want to continue having informal discussions. Otherwise, we will meet again next Friday at 9 o'clock, and Kusha Etasami will give a talk on finding fixed points for in lattices, right? The complexity of finding fixed points in lattices. We can still take some questions, but if there are no other questions, thank you, Orna, and we adjourn to the gather or to dinner, I guess. Thank you.
Thank you.